Could you though, please?
Okay. Whoa. You guys. Whoa. Okay. Now. All right. So this is. They're all pointing north, and then we're going to turn on a circuit, have current go through, and now the red arrows are pointing in a circular pattern around the wire. So, may I introduce you to right hand rule number 1. This is kind of like your secret handshake in physics. Okay, what you're gonna do? Your thumb represents the direction of current. Oh, you can't see any of that. Okay, the thumb represents the direction of current. Okay, and your fingers represent the direction of the magnetic field going around that wire. Okay, so we're grabbing this wire, sticking our thumb in the direction, sticking our fingers in the direction of the way the compasses are pointing, and that's going to show us the direction of current in this wire. Okay, does that make sense? So there's current going up through the wire. Okay, this was actually discovered by a high school physics teacher, probably messy, I'm assuming, and was doing circuit projects and had compasses lying around from the last experiment, and he turned on the circuit, and he noticed there's a deflection in the compass. He's like, what? And that's how we discovered that moving charged particles create a magnetic field. Okay, so what I want you to do now is hypothesize, if I switch the direction of current, which way are the compasses going to point? Okay, so observe and go sit down. Get it right. Like try it with your right hand, and then have a seat. Cycle through, then have a seat. Okay. By the end of this lesson, you'll be able to describe fundamentally what creates a magnetic field, describe the magnetic field formed by current flowing through a wire, draw and interpret vector arrows going in 3 dimensions, and describe the magnetic field formed by current flowing through loops of a wire. Okay? Foundational fact number 1 says moving charged particles create a magnetic field. This is like, why? They just do. Okay? We've observed it to be the case. Okay, so moving charged particles create a magnetic field. Where do we find a lot of moving charged particles? In circuits. Good with that? So we just demonstrated that. Okay? Moving charged particles create a magnetic field. All right? So we just did that demo. So if you could see the magnetic field, it goes all along the wire. Okay? And it gets weaker as it goes out. Like the lines are closer together here. Good with that? Okay. So figure out which way magnetic field is pointing with current going down. Tell your neighbor. Okay, correct answer is A. Everybody okay with that? Pretend your pencil is the wire, and grab the wire with your thumb going down. Your fingers are going in the direction of the magnetic field. Okay? Embrace the right hand rule. Okay? Everybody's doing it, man. Everybody's cool. Okay? So now, physicists not so good about drawing three-dimensionally. So we have come up with this notation. It's the same exact scenario, but I'm just representing it with circles with dots and circles with X's. Dots and X's. Circle, did you do the pre-quiz? Tell your neighbor. Explain it to the person who doesn't know. Okay. Circle with a dot. This is like an arrowhead coming at you, like, duck. And you're like dodging. Okay? Like a bow and arrow. Okay? This is, you're looking at the tail feathers. As it goes away from you, we say into the page. Good with that? Okay? So this, your fingers are coming on the right hand side, are coming out of the page. On the left hand side, they're going back into the page. Good with that? Okay. Give that one a shot. Have a conversation. All right. Here's another way you can look at this. So you got your pen. You're going to grab it with your thumb going to the right because that's the direction of current. Your fingers are wrapping around this way. Pretend you are spinning a tennis ball on a string in the direction that your fingers are going. Okay? If you would let go of the tennis ball at point P, which way would the tennis ball fly? It would fly tangent to the circular path out towards us, F. Does that make sense? Good with that? Next question. You might need actually just buddy up with somebody. Two right hands. You need two right hands. Buddy up. It does not work with a right hand and a left hand. You need two right hands. One person be one wire, one person be the other wire. So I want to know what's the direction of the net magnetic field at point P. Correct answer is? You guys did not do a very good job convincing each other. Okay, this one. I'm grabbing the wire with my thumb going up. At point P, my fingers are going into the page. Does that make sense? Into the page. That's how we say that. Okay. Here I'm grabbing it with my thumb going down. At point P, the finger's going into the page. Okay, correct answer is A. Both are going into the page at point P. It is not clockwise, counterclockwise. That is not what we are looking at. We're looking at which way is it going at point P. Good? Okay. Now, if I turned off the current in wire on the right-hand side, what's going to happen to the net magnetic field as a result of that compared to this? Tell your neighbor and tell them why. Correct answer is B. Why? We had two magnetic fields going both into the page. We turned this one off, and that took care of one like that and made it weaker because now there's only one going that way. We would add those together when they were both on because they're both going in the same direction. The magnetic field is going in the same direction, not the current, but the magnetic field at point P. Okay. Now I'm going to switch the direction of current in the right-hand wire. Both are going up. Yeah, the current is both are going up. Whoa, whoa, in your brain, in your brain, in your brain. See if you can figure it out. Just by yourself. Oh dear. You need that. You're gonna die without that thing.
I might. I mean, if I can't, I don't want it. I might die.
Yeah. Tell your neighbor. Tell them why. It would point directionally north because it wouldn't be influenced by that.
So we should have like two really strong things like that. And put a magnet in the middle.
Would it float? No, it would not float. It wouldn't do anything because the net magnetic field is zero.
But they're both holding it from falling.
No, they wouldn't be.
Okay, if you put a wire and you put a magnet, would it like go into orbit around the wire?
No.
So then what do you mean? How would it, if the magnetic pole is in a circle, then why wouldn't a really like small magnet like go into orbit?
Just put some disgusting pieces of gravel. But like you had like a magnet below too.
If you
It was close, but then it was.
okay, so you get okay. Let me answer this, then I'll get there. Okay, correct answer here is what? Good. So good with that? Okay. If there was a single wire, and there wasn't any gravity or anything else, it was just a single wire with a and then a miniature magnet, like a compass. What would happen? I think it would just be attracted. I don't think it would orbit.
But then wouldn't the magnetic pole be going towards the wire, not around it?
So the field would be going around it. The pole would be the total. You'd have to kick it off to make it go in a circle.
Okay, so say we put a string on top of one of those wires, attach it to a magnet, put it on the outside, and give it a little push, it would circle around.
Yep.
I think we should try that.
We don't have no gravity.
Well, that's what the string is for, to hold it up.
Oh, no, then it'd just be like a tetherball. And it'd do that anyway.
That's what I'm saying, so it'd do like that.
Yeah, but it wouldn't be because
Okay,
of
so
that.
say you put like a magnet on top and a magnet on bottom, they're holding each other up. Or a magnet on bottom, a magnet on the ground, holding this other one in the air, and then you gave it a little push, and then like you had a magnet on the bottom.
If you
like magnets
set
on
that up, bring it in, and we'll check it out. All right, check this one out. To point P over here. Current going up, current going down. Point P is off to the side. Tell your neighbor. Tell your neighbor why. Correct answer is B. And then if we turned off the current in the right hand wire again, tell your neighbor why you think so.
The other side is like, the other side is going down, so it's like going this way, so like the farther away it gets, like the weaker it is, but it's still effective, like the.
Okay.
It's like strong.
Correct answer is A. Gets stronger. Okay, so here, this guy is creating a magnetic field coming out. This one's creating a magnetic field at point P going in. It's just weaker because it's further away. They're going in opposition, in opposite directions. This one's creating going out, this one's going in, but this one's, the end's weaker, so it added up, it's still going out. You turn this one off, you don't have that weaker one, so it gets stronger just with that single wire. This is not fighting against the magnetic field of the right hand wire. Good? Okay. If I arrange that wire in a loop, I made the loop square for your convenience. My recommendation would be look at each side. Take each side separately. Grab the wire on the left side, top, the right side, the bottom, and evaluate at each of those sides the direction of the magnetic field. Tell your neighbor. Okay. Correct answer is B. If I look at the left side, I'm going to grab, here's my wire on the left side, I'm grabbing that with current going up at point P, going into the page. Top. Thumb's going to the right, fingers going into the page. The right hand side. My thumb's going down, direction of current, fingers going into the page. Here at the bottom, thumb's going to the left, fingers going into the page. Each side's going into the page. So, which do you think is stronger? Magnetic field inside a loop of wire or alongside of a straight wire? Is everybody okay with the loop of wire? Okay. You got 4 things contributing to the magnetic field versus just one. Okay. That's a crazy thing. I just put a loop of wire. I put a loop in a wire and I get a really strong magnetic field on the in the middle here. Now, we don't usually make square loops. That was just for your convenience. Usually it's just a circle. Okay. We'll get a really strong magnetic field in there. That's a crazy cool concept. Like just like boop, strong magnetic field. Okay. So what we do to figure out the direction of this, here's a loop of wire. You're going to look at the part of the loop that's closest to you. This one's further away, three-dimensionally. This one's closer. We're going to grab the closer one with the thumb in the direction of current. Current's going this way through this wire, and I'm grabbing this, okay? I'm going to look at which way the magnetic field is going inside the loop. Okay, it's like a lifesaver. You're going to stick your fingers through there like, help me, okay? The magnetic field's going up through here. Does that make sense? Okay, what we care about is inside the middle there, okay? So here is just a plane of the magnetic field in a loop of wire. So you kind of have it circular. Does that kind of make sense how that's working? Okay, but really it's three-dimensional. Okay, so it gets really strong in the middle there. Good with that? Okay. So this is this part here. You're just looking at the side view of that. Come on over here. Everybody's going to come over here in a second. What?
I was wondering what else was.
Yep. Have a conversation. What? You're good right now. You just pay attention. Here, sit over, like, hang out over there, and you can see what I'm doing. Correct answer is B, to the left. You're going to grab this part of the wire with your fingers going down in the middle of the loop here. That makes sense? Grabbing that, your thumb's going to the left. So current's going around like this. How are we doing with that? Now, we can do some crazy cool stuff with that. Come on over here. Actually, no. Yes. Don't go in front of this first row. Stay back here so everybody can see. So it's not dangerous. I just want everybody to see it. Okay, what I have here is a loop of wire. It's a single wire wrapped a whole bunch of times in a loop. Okay. And what I'm going to do, I have it hooked up. I'm going to stick compasses in here. Which way are the compasses pointing? Can you see that? They're pointing north, as they should. Okay. Now, when I know you can't, just trust me on this one. They're pointing north. Okay. When I turn on the current, oh boogers, I got a renegade. Here, let me tell you the magic here. So this compass is wrong. I'm going to fix it by rubbing it like you rub the magnet. All of a sudden it works right. Never trust a compass in the classroom of physics. Okay. So now I'm going to turn on the current, and they're now both going that way. Can you guys see that? The compass arrow? Okay. I want to know which way the current is going through these wires. Is it going this way or that way? Does everybody see the arrows? Okay. Which way is the current going through these wires? Is it going this way, up, or this way, down? If you're not using your right hand rule, you're just talking outside your head. You're like, I think it is. Like, verify, prove it. Okay. Your fingers are going to go this way. You're grabbing this. You're looking at the part of the wire, the coil that's closest to you. You're grabbing that. You can't grab the wire like that. You can only grab it like this. Okay, so current's going up through these wires. Yes? Okay. Now, I'm going to do some iron filings here. And we're going to check out what the pattern, this is a little harder to show sideways. Can you guys see that? How they're lining up? Ah, bluefish. Does everybody see that? How they're lining up? They're going that way. Okay. Now, here's a crazy thing. If I take a piece of steel that has iron in it, I stick it in here, and I turn on look at the end here. Get at that. Now if I turn okay, if I turn off the current, okay, so I cause some of the domains to actually permanently go that way. But it did get weaker. Did you see that? How when I turned it off, some of the iron filings dropped. Okay, so I have now, what do I call this? Like the fact that I can turn off and on a magnet. What is that? An electromagnet. Okay, so if I take this and beat it against something. People below me don't like me. Okay, if I take this, I hope it's still magnetized, but not as much. Okay, does that make sense? So if I turn that back on, okay, good with that. Okay, now where do magnets come from? We make them. This is a magnetizer. All this is are coils of loop, the coils of wire wrapped around each other. Okay, and what I do is I put south in there and north in there. Press the button. That allows current to go through it. Okay, and I test this, and it works as we anticipated it would. But what happens if I stick the north end where the south end should have gone, and the south end where the north end should have gone? And then I press the button. Don't do it, don't do it. Just did it. And now I just flipped the magnetic poles of that magnet. Okay, that's not what it should do. Okay, you good with that? So make sure I magnetized that magnet incorrectly. I'm going to correct that now. And it does. It's just a momentary, like, so it doesn't stay on.
So if you have to keep pressing the button.
Yeah.
Can we do that?
I mean, at some point. I mean, it's sure. All right, have a seat. Okay, so here we have a solenoid. Okay, it's just a coil of loops. You get a really strong, John, Sam, John. We have a really strong magnetic field in here. Get us that? Okay. So here it's a plane kind of looking at the sheet with the iron filings, but in reality, it's going to be three-dimensional. Okay, and we get a really strong magnetic field in there called a solenoid. Okay. So on this question, I'll give you a hint. It's not a right-hand rule thing. You're just looking at the magnetic field. Tell your neighbor what you think. Tell them why you think it. Correct answer is okay. So correct answer is A. Okay, so outside, catch this, outside the magnet, magnetic field lines go out of north into south. Inside the magnet, it goes from south to north to make a complete loop. Good with that? Okay. This does require the right-hand rule. Grab part of the wire, the loop that's closest to you. Have a conversation.
Inside the neck.
Correct answer is? Correct answer is C. Crazy cats. Okay. You grab. This is the part of the wire you look at. It's closest to you. grab it with your thumb going up in the direction of current. You put your fingers inside the loop. Fingers are directed to the left. C. Good with that? Give that one a shot. Have a conversation. That seem doable.
What?
These things.
Yeah.
Sure. There's a little funnel right there. Little hole. Correct answer is. Correct answer is A. Okay. Here, I want this to be north. So I want magnetic field lines to go that way. Okay. So my fingers, I want to go up. Thumb's going to, I'm grabbing this part of the wire. It's closest to me. Current's going that way. Good? Okay. So an electromagnet, you just stick this would be an air core electromagnet. You can stick a piece of iron in there just like we did the wrench and make it stronger. Okay, you might have done that in like middle school, make an electromagnet with a nail, wrap a nail with a wire, hook it up to a battery. Good with that? Got a pre-quiz due tomorrow. Pre-quiz, another one. Oh yeah.